So, good evening, everyone. Uh, my name is Debanjan, and I will be taking this live sessions for the course of Joining Technologies for Metals for uh, each week, Tuesday from 6 to 8, as you know. Uh, I am a PMRF research scholar at the Department of Mechanical Engineering, IIT Kharagpur. So, how will we proceed is like that. You are going through your lecture videos of the professor, right? So Professor D.K. Dwivedi is taking the course, and we'll be going through all those video lectures initially. So what I will do is we'll have very brief discussions of what was covering in the earlier lecture videos, and with some question and answers, right? So during the meantime, we will have some questions and answers, what we will try to answer, and during answering those questions, we will try to recapitulate all those all those fundamentals of whatever was covered in those earlier lecture videos, right? So that's how we will proceed throughout this course. And I expect all of you please attend these live sessions. It should not happen like uh, because I will be uploading these videos every time in YouTube, and of course you will have some access afterwards, but I expect all of you to join these live sessions for each Tuesday and have a fruitful session, right? Okay. So in the week one lecture videos, it was very basic, right? So we have gone through some introductory lecture videos on joining aspects, what happens during welding, some fundamental mechanisms of welding, some classifications of joining process based on uh, different classification strategies. Uh, then we have gone through some heat generation process in welding, right? How heat is generated in welding. So we'll not go into very detail in our first session. Basically, it will be covered whatever has been covered in your earlier uh, week week one videos, and then some aspects on protection of weld metal. So these aspects have been covered in the uh, week one lecture videos, right? So we'll go through one by one. We'll try to go through one by one very briefly, right? I'm audible, right? Uh, Sorry. My connection got lost. My connection got lost. Sorry. Am I audible now? Yeah. Thank you. Thank you. Connection is very poor. Okay. So what is joining process basically, right? Um, if you see the manufacturing process which are employed to produce a single component, uh, joining process are used to assemble different members, right? you are assembling different members to yield some desired complex configuration, right? So the complex geometry which are either too much difficult or impossible to obtain by using some other manufacturing process like cutting process, machining process, uh, which you have gone through, right? So in joining process, those are intimately related to the overall production system that they are considered a class of manufacturing technique, uh, which can be either temporary or permanent in nature, right? So your joining process can be either temporary or permanent in nature based on what joining process you are going through. Now, it depends on your mechanism of bonding, right? It can be either mechanical bonding or it can be atomic bonding. So all the joining process which involves this atomic bonding are permanent in nature, right? Now we will discuss this principles and mechanism of all such processes, and in doing so, uh, we will consider different physical, different mechanical, and we will try to see different metallurgical factors also, uh, which will govern those quality of joints, right? Now, what are the criteria which can be used for classification of joining process? So if we So initially, I will just have a very brief introduction on this joining process, and then we will go through this question and answers, right? So if we see this scheme or criteria of a joining process, so let me write down. So what are different criterias by which you can classify a joining technique? So you can group three different categories. So you have autogeneous, you have homogeneous, or else what can you have? Any answer from anyone? You can have autogeneous welding,
Heterogeneous.
right? So you can have heterogeneous. So you can have three different categories of welding: autogeneous, homogeneous, and heterogeneous. Now, when when you are not using any kind of filler metal, right? So when there is no need to use filler metal in your joining technique, that will be named as autogeneous welding. So what are different kinds of autogeneous welding? All types of solid phase welding or resistance welding, those are examples of this category. So filler metal is not used over here. Filler metal is not used, right? So all kind of solid state weldings can be referred as your autogeneous welding. Now, what happened in homogeneous joining technique? So in homogeneous joining technique, uh, do you need filler metal? It is required or not required?
Required.
In homogeneous joining technique, you require filler metal. Now, the filler metal what you want to use, that will be of same category of the parent metal what you want to join, or it will be a different metal in homogeneous joining.
Same category.
So my filler metal will be of same material, be of same material, as of the parent metals to be joined. So the reverse is true for the heterogeneous. The filler metal, whatever you will use, that will be of different material. What you are trying to join as a parent metal, the filler material will be of different material, right? Now, can you name few examples of homogeneous joining? So you can have arc welding, you can have gas welding, you can have. So these are fusion welding techniques where you are using some kind of filler metals, uh, where filler metal will be of same material as of the parent metals to be joined. Now, can you name few heterogeneous joining techniques where it will be of different metals or different materials? So basically what is happening over here, the two materials, those are insoluble in each other. Let's say you are joining iron to silver. So they are insoluble in each other, right? So there will be some nucleation and growth. So these are solidification mechanism, right? Through which you can control your microstructure. So the materials which are insoluble in each other, let's say aluminum, copper, or iron, silver, those can be joined by this heterogeneous process. Or let's say copper tin, right? So copper plus tin, iron plus silver. So there is soldering technique or brazing technique, right? Where your joining will be heterogeneous in nature. My filler metal, the material combination will be different, right? Now, what you what will govern your welding quality? So my welding quality will be governed by how much strength is there in your welding, right? So the bonding force between these two metallic atoms, you know that it decreases sharply with that interatomic distance. So if your interatomic, so I'm little bit diverging, but yeah, interatomic distance, if it is increasing, bonding force will get reduced, right? If you are increasing your interatomic distance, so the bonding force between those metal atoms will decrease very sharply. And when the distance is more than a few atomic spacings, maybe let's say few angstroms, the interacting attractive force they reduces to almost zero, right? So the force increases sharply and attains a very large value when the distance is reduced. So this is if you are trying to understand the mechanism from an atomic scale, that is happening in terms of atomic scale, right? Now, if you are trying to if you are trying to bring two metal atoms together, if you are trying to bring this, let's say, two metal atoms together, there will be two metallic surface, right? So there will be this atomic surface that will come together. But so basically, what is happening? Some kind of grain boundary is forming, right? Some kind of grain boundary is forming which is separating them, and those two bodies will adhere with very large force, resulting what we call welding. However, in normal atmosphere, those metal surfaces are contaminated with layers of oxides, or there can be adsorbed gases. So these layers are normally a few hundred angstrom thick in nature. So it is not possible to generate a strong attractive force when two metal surfaces are brought into contact in room temperature, right? So in room temperature, there will be oxides, adsorbed gas layers, etc., which restrict joining, right? So how can you eliminate those things? So just a moment, what happened? Yeah. Huh. But this difficulty can be eliminated when those contaminating layers are removed from the surfaces. So this may appear as a problem for welding. These oxide layers always appear as a problem for welding, right? You have to somehow get rid of those oxide layers. Uh, it can be by some kind of polishing, some kind of scratch brushing, so that those oxide layers you are removing before joining takes place. Uh, like whenever you are joining some aluminum metals, they have great of affinity to react with oxygen, right? It will never happen that you are not getting oxide formation when you are joining aluminum. It has great affinity with oxygen. It can react very easily, even at room temperature. So basically, you cannot eliminate oxides, but what you can do is you can reduce the formation of oxides by doing some protection in your weld atmosphere, right? Those things will cover in the due time, right? Now, what are different classifications of joining process? So we have talked about. Let me write down. We have talked about atomic bonding, which is permanent in nature. This is permanent in nature. And what else? This is mechanical. So in mechanical, how you can join, it can be temporary or it can be permanent. What are different kinds of temporary joining techniques? So you can have some screw elements, right? You can have some nut bolt assembly. Those things are there through which you can assemble, disassemble different mechanical components. Maybe those are easy to handle for different applications, but not true always. Now, what are different permanent mechanical joining techniques? We can have rivets, right? You are aware of these things. You can have rivets, you can have some string fitting, you can have some kind of stitches. So these are some permanent kind of mechanical joining technique. We will mostly be with this atomic nature of welding technique, right? So we will discuss all over this course about how diffusion is taking place. If you are talking about atomic scale, atomic diffusion is happening, right? In each and every joining techniques. So there can be solid state welding. There can be liquid state or fusion. or what else? You can have solid liquid, right? Now in solid state welding, can you name few solid state welding techniques?
Friction welding.
Okay, friction welding is one of those. Anything
Sir, what
else?
is shrink fit?
Anything else? Anybody have any question?
Yes, sir. What is shrink fit?
Shrink fit. So I would say that string fitting is kind of a technique. You can say it as an interference fit. So string fit. So you are aware of interference fit, right? So there are different fits: clearance fit, interference fit. So this is kind of interference fit which can be achieved by some kind of size change after assembly. So it can be usually achieved by heating or cooling one component before assembly and allowing it to return to ambient temperature during cooling after assembly. So based on that contraction which will take place during heating and cooling, it will tightly fix one component over other. This is kind of permanent joint. So if you are heating a material, so let's say uh, initially it was smaller dia compared to this, and then you heat it up, it will try to expand and it will kind of lock in between. So you can think it of as an interference fit. Okay,
Yes.
people usually do this induction heating technique to preheat your metal component between somewhere around uh, 150 to 300 maybe, and causing them to expand and allow for the insertion of or removal of some other component within that component which you are induction heated, right? Okay, so we are in solid state welding. Friction welding is one of the solid state welding technique. Anything else? We have friction welding. You have heard of diffusion welding, right? Diffusion welding itself is a kind of welding technique. Although each and every joining technique is having some kind of diffusion taking place, some kind of atomic diffusion taking place. However, diffusion welding is a by itself it is a different what should I say? Some different weld configuration is there for diffusion welding. You need some uh, you need some punch, you need some vacuum, you need some vacuum atmosphere so that you will keep it at certain temperature below the melting temperature. You will apply some pressure. So diffusion will take place in solid state for long amount of time. So in solid state, diffusion takes a lot of time, right? What is diffusion? You have heard of diffusion length, right? You have heard of diffusion length. So something like this. So there is some term called diffusion coefficient. There is some term called diffusion time. So how fast diffusion is happening for how much time? More the time, diffusion will take place more. Diffusion depth will be more. So this is my diffusion depth. More the time, there will be more amount of diffusion. So depth of diffusion will be higher. And what will happen if diffusion coefficient is higher? It will act as a faster reaction rate, right? So if diffusion coefficient is higher, diffusion coefficient, diffusion coefficient governs your rate of reaction. So in liquid state, your diffusion coefficient will be much higher than your what will you will see in solid state. So diffusion takes place very quickly in any kind of if there is any kind of melting happening. So at solid liquid interface, diffusion will takes place very quickly, right? Okay. So there is something called cold welding also. So in cold welding, you can think of some. You have heard of ultrasonic welding? Have you heard of ultrasonic welding? Yes or no?
Yes, sir.
So what happens in ultrasonic welding? By the name, what does it tell you in ultrasonic welding? You will have some high frequency ultrasonic acoustic vibration, right? Which you can apply locally to a workpiece which are being held together under pressure. So you'll have some kind of horn like this. So horn design is very critical thing for ultrasonic welding. You will have those metals together. So only lab configuration is possible. Just keep it in mind. Only lab configuration is possible in ultrasonic welding. You'll have some anvil kind of thing. You'll apply pressure, and along with pressure, you'll have some oscillatory movement, high frequency oscillatory movement. Because of that, you'll have some cold deformation or some kind of breakage of oxide layers. So whenever you are thinking of any kind of surface, it is not appropriate, right? It is not smooth all everywhere. There will be, as I was mentioning, there will be oxide layers, there will be adsorbed gas layers. So you need to break those things. So if let's say these are my two interfaces, it will break oxide layers over one place, it will break oxide layers over this place, and there will be formation of metallic bridge. More you apply pressure, the contact area will get increased, right? Okay, so yeah, there is this ultrasonic welding. Then also you can have explosive welding also. Have you heard of explosive?
Yes, sir.
What happens in explosive welding?
Some nuclear reaction.
Hmm. Uh, I could not hear you.
And so in explosive welding, basically some reactions took place at a very fast rate, and due to that, heat doesn't get dissipated because within a very short interval of time, heat doesn't get dissipated, and because of large pressure, two seats got joined.
Right. So it is mostly used if there is application of some kind of cladding of some metals. Let's say you want to clad steel, carbon steel or aluminum plate of a thin layer, right, over some other material like uh, so. This is basically used for some cladding purpose, and this is a solid state process where you are accelerating one of the components. So strain rate is the critical factor over here. So now means if you are thinking of yield stress of a material, or if you are thinking of a plasticity of a material, yield stress is a function of what variables? It's the function of strain rate, and temperature, right? So if you are changing your temperature, your yield stress will vary. If you're changing your strain, your yield stress will vary. If you're changing your strain rate, your yield stress will vary. Now, for explosion welding, or if you're thinking of some kind of uh, some kind of collision, which is very or some kind of impact, right? Those are high strain rate processes. So with high strain rate, severe plastic deformation takes place at very minute amount of time. So there will be large amount of strain rate, and because of that there will be temperature generation, and because of which there will be softening of metals, and those aspects are there, deformation based process, softening of metals, and it will join over the other metal, right? So explosion was there. Then in we were in solid state welding. Then in liquid state welding, let me remove this. What are there for liquid state welding? In terms of heating source, you can have different heating source, right? You can have electric heat source, or else you can have chemical heat source, right? Now electric heat source, of course, you know there is arc welding, there is resistance spot welding, there is induction welding, right? So you have arc, you have resistance spot, you have induction welding, and for chemical reaction, what do we have? We have gas welding, we have thermic welding. So there is this two welding categories when there is when you are using chemical heat source. Now let us try to understand principle of solid phase welding. I was talking about through. I just removed that figure. Anyhow, let us try to understand the principle of solid state welding. What is happening over there? So whenever two metal surface they are brought into contact, the real contact takes place through a small area of asperities, right? So as I was saying, your metal surface is not, the surface finish is not always higher. So you'll have some kind of asperities like this. Over here, there will be asperities like this. Enough. So this metallic bridging occurs even in the presence of uh, these adsorbed surface layers or oxide layers. So you are trying to connect with one another. You are not applying pressure now, and these bridges formed have the property of a, you can think of a grain boundary, right? So these bridges are stronger than the bulk metal. So whenever they connect with one another, so metal bridges are stronger than the bulk property of the metal, right? Why? Because some kind of work hardening takes place when you are applying pressure in those layers. So just beneath the melting surfaces, there will be some kind of work hardening taking place. So I am using these terms which are, I hope these are familiar with you, right? Some kind of
Yes, sir.
strain hardening or work hardening taking place along those metallic bridges, right? Now, if the yield strength of the material is, let's say, sigma y, with the applied force as, let's say, PE, so let's say my stress is sigma y and force is PE. So what will be the area of contact? What will
PE
be my
by
area?
sigma y.
So it is PE by sigma y, as simple as that, right? However, around this welding zones, there will be some areas which come in contact, but the stresses are still within the elastic range, right? So experimentally, it is suggested that including those areas, the total area of physical contact with a moderate external pressure can be taken as 2 Pe sigma y. This is some experimental finding, or let's say this is true from some experimental finding. Now, when the applied load is removed, these two surfaces separate out only when the elastic forces trapped in those regions around the bridges, they're strong enough to break apart those metallic bridges. You know? So it is seen that softer the material, better will be the adherence. So it is seen that this is seen from researchers, right? So what are the factors which is governing the solid phase welding? So you'll have the surface deformation, you will have some kind of diffusion, and finally you can have some recrystallization. Are you aware of recrystallization? Yes or no?
Yes, sir.
Okay. So you'll have some kind of surface deformation, then you can have atomic diffusion in solid state, then you'll have some kind of recrystallization. So we'll not go into all those details anyhow. So surface deformation is during welding is difficult to measure. Uh, as such, in pressure welding, the bulk deformation is used as an index for surface deformation. So the thickness reduction of whatever is happening over there, right? So deformation can be measured through this calculation, right? In rolling, you are familiar with this equation. For a circular specimen, how will you define this deformation index? So it will be the dia. Dia is important over there, right? So strength of a weld junction that increases with increasing bulk deformation. You know? Moreover, below a certain critical deformation, you will see there will be no weldment which will take place, right? So amount of deformation is necessary for obtaining some specific strength, right? And also the specific strength decreases with increasing temperature. So a strong weld may be made with only 10% deformation if the work temperature is quite close to the melting point of the material, right? Okay. So this is something on yeah, one thing I want to mention again. The greatest hurdle in solid phase welding is caused by what? Oxide layers or those oil films, right? Those can be removed by heating in hot welding or by means of I was mentioning those scratch brushing in cold welding, right? Those can be reduced to a certain extent by scratch brushing. Of course, it cannot be removed completely. So these oxide layers are hard and brittle in nature. So always those oxide layers, please be on time from next sessions on. So oxide layers are hard and brittle in nature. What will happen if it is hard and brittle and you are applying pressure? What will happen when it is hard and brittle? So fracture will take place very easily, right? When you are applying pressure to a hard and brittle metal, there will be easy crack propagation or some fracture initiation and propagation will be very easy for a brittle metal, right? Okay. Now, what is there in terms of fusion welding? So uh, in fusion welding, the material around the joint is melted, right? In both the parts to be joined. So whatever material you want to join, those will be melted. So if necessary, I was talking about you can use a molten filler metal if you want to add it. Now this can be either autogeneous or homogeneous. So what are different regions of a weld metal? What are different regions of a weld metal? So I am going a little bit into the metallurgy part. Okay. So let me take. Why don't we why don't we initially do some question and answer? Let's do some question and answers. And then we'll again discuss later on if there is time. Okay. So mostly we will have some kind of MCQ questions, which will be very basic, and also I will try to add some numericals during those sessions. Okay. So in question one, it says heat in welding is required to this oxide decomposition, lowering in strength, retarding the diffusion, and dynamically recrystallize the grains. Can you tell me which one will be the right one? Simple. Heat in welding is required. Is it required to lowering the yield strength? So why don't you try first? I want some answers. Hmm? Can be wrong, na? Just give some answers. Heat in welding is required to. What do you think? Why heat is required in welding?
So option B,
Option.
lowering the yield strength.
Uh, so of course, if you apply heat, there will be lowering yield strength. But the glitch is over here. There will be no restricted deformation, right? The deformation also will be, or it should be large enough to generate good bit of heat in welding. So one is oxide decomposition happens when you apply heat. So A is true, and also the D to recrystallize the grains, right? Now in question 2 it asks why pressure is required, fracturing brittle oxide layers, keep the absorbed gas layers. Of course this is false. Increase the surface area by forming metallic bridges. Yes, this is true, and this is true. So A and C, right? Agreed?
Yes, sir.
What about the next?
B, option B.
Option? Option?
B.
Option B. Right. So B is correct. No, thermic welding is a thermochemical process or some kind of chemical reaction takes place, right? So it utilizes a chemical heat source, which is normally used for some on-site welding of uh, rail application, right? So here the temperature will be obtained much higher than the necessary or the reaction product that is iron, right? Yeah. So thermic welding is a thermochemical process and electrogas welding is an arc welding process. Are you aware of electrogas welding or electrogas? This is also called electrogas arc welding also. Are you aware of this? This is a vertical position arc welding process, right? So here arc will be stuck between a consumable electrode and a workpiece. You can use a shielding gas, but pressure is not applied over here. So major difference between uh, electro gas arc welding and electro slag welding is that arc in electrogas welding is not extinguished but instead remain stuck throughout the welding process. It can be used to make some square groove welds, maybe for butt or T joints. Especially in shipbuilding industry, they use this vertical position arc welding. Right? Okay. Next, in question 4, I ask, during the solidification of a weld metal, nucleation and growth mechanisms are observed. Which of the following is true? For autogeneous, for homogeneous, or the heterogeneous? Anyone?
Heterogeneous. Option C.
Hmm. I want some answer from other candidates, please. It's not exam, right? Please participate while we'll have this question and answer round. So, yeah, when this filler material of composition will be different to base metal, which is a heterogeneous process, you'll have those nucleation and growth mechanism. I'm not going into detail of that metallurgical aspect of that mechanism, what happens during nucleation and growth anyhow. So, whenever your two metal or two atoms are insoluble in each other, they will try to segregate, right? So if you are allowing time or if you are allowing time for diffusion to happen, whenever the mixing takes place, there will be segregation of those mixing or allowing things, they will come out and it will nucleate in terms of a microstructural thing. So, okay, leave it. Now, in question 5, uh, there is some statement provided and there is some reason provided for that statement. We need to tell, is the statement true and it is the correct explanation or not, right? So this asks about the electron beam welding. So let us briefly talk about what happens during electron beam welding, and then uh, maybe during the discussion itself we can have the answer. So what happens in electron beam welding? Of course, there will be melting, and the joint metals, the joining is taking place by heating the metals with an electron beam, right? So there will be a cathode of electron beam gun which will be negatively charged. So let me try to draw. Let me try to draw. So how should I draw? So let's say I have, sorry. So this is cathode. Here I have my electron beam like this. I will have a focusing coil. I can have, I will have an anode over here, right? And if this is my specimen, it should be kept in vacuum. So the session will be starting from 6 to 8, right? The session is from 6 to 8. So from the next day onwards, please try to be on time. So, yeah, as I was mentioning, uh, the cathode of this electron beam gun will be a negatively charged filament, right? This is a negatively charged filament, and again, I will make some term. I hope somewhere at some time you have come across this term thermionic emission. So whenever the temperature is above this thermionic emission temperature, the filament will emit electrons, right? And these electrons will be accelerated by the electric field between a negatively charged electrode. So you have a negatively charged bias electrode, which is slightly below the cathode and the anode, and they pass through the hole in the anode and are focused by some electromagnetic coil to a point at the workpiece surface, right? So what is a typical current of electron beam welding operation, or typical voltage of electron beam welding operation? At least the order of current and voltage. So in electron beam welding, you will work in a milliampere range, right? It can have some 50 milliampere to 1000 milliampere with some kilovolt voltage order. So it can have some 50 to 150 kilovolt. So this is some typical range of electron beam welding operation. So electron beam of very high intensity can vaporize the metal and form a vapor hole during the welding, right? So it is called keyhole, forming a keyhole over there. So the notes what I'm making is very random in nature. Anyhow, we'll have the video lectures afterwards. So uh, I was mentioning that keyhole
But
operation.
can we get PDF of these notes?
Sure. Both the things will be shared. But in PDF, basically I just removing things, deleting things again. I'm writing. So fine. Whatever will be convenient for you, that is okay. Both PDF and videos will be shared. So yeah, an electron beam of very high intensity that can vaporize the metal and form a vapor hole during the welding, right? So uh, this beam diameter that decreases with ambient pressure, right? Electrons can be scattered when they hit air molecules, or when the pressure will be ambient in nature, right? So lower this ambient pressure or more the vacuum will uh, make those electrons less scattered. That is the main reason for EBW to uh, conduct in a vacuum chamber, right? Now, what is a typical range of diameter where this beam can be focused? These are some millimeter range, maybe some 300 to 800 micron. So 300 to 800 micron diameter. This is a typical range over which this electron beam can be focused. What is a typical order of a power density for electron beam welding? This is in the range of some 10 to the power 10. This is very high, right? So this very high power density makes it possible to vaporize the metal and produce a deep penetrating keyhole and hence the weld, the final weld. Okay? Yeah, yeah. So if you see a single pass electron beam and if you see a dual pass uh, gas tungsten arc weld, so it will you'll see it like this, the weld profile. This is for electron beam welding for a single pass with very large power density. On the other hand, the gas tungsten arc weld will be much more wider, much more spreaded in nature with uh, high amount of heat affected zone, right? So this is very narrow in nature. The heat affected zone will be very less, right? So energy required per unit length of the weld which is much lower in the electron beam weld than in the gas tungsten arc welding, right? So yeah, 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 that is the part. So what is the advantage and disadvantage? So with a very high power density in EBW, full penetration K1 is possible even in thick workpieces, and joints that require multiple pass arc welding that can be welded in a single pass at high welding speed in EBW, right? Because because the heat affected zone is very less with much higher intensity, the welding distortion is very less in electron beam welding. So there is this answer for this question. Now tell me which one is the true. Which one is the true? So we say that distortion present in electron beam welded sample is less as compared to other welding processes. Is this true or false?
True.
This is true. Okay. And is this right reason of this statement? Electrons with high velocity impinged on the surface of the material. It is transferred to the heat and induces a maximum amount of weld penetration with the less amount of heat. Yes, this is also true, and this is the correct explanation. Okay. Uh, One thing I want to mention over here, I was talking about this power density, right? So, yeah. So let's consider directing us a some 1.5 kilowatt hair dryer very closely to a stainless steel sheet of some 1.5 mm thick stainless steel sheet, right? So what will happen? Basically, the power will spread out over an area, right? Over an area, it will spread out, and the sheet just heats up gradually, but it will not melt, right? Now, if you are using some kind of gas tungsten arc welding, or I will not go to this uh, EBW thing, of course. Now, for gas tungsten arc welding at some 1.5 kilowatt, the power is so much. Uh, if you concentrate on a small area of about let's say some let's say some 5 to 6 mm, what will happen? It can easily produce a weld pool, right? So heat source for gas, arc, and this high energy beam welding process, those are gas flames, electric arc, or a laser beam or electron beam, right? So laser beam and electron beam are high energy beam welding process. Here the power density increases from a gas flame to an electric arc and some high energy beam. So if we try to draw some graphs of how does it look like in terms of power density. So this is my power density. This is my heating to workpiece. So let's say this is gas welding. But the heat input to the workpiece is very high, with a very low power density. Arc welding stays in the middle compared to the high energy beam welding process. Like laser and electron beam. Right? Okay. Can you tell me can you tell me any kind of chemical heat reaction, or how does it happen in terms of chemical heat source, or what happens in, let's say, gas welding? Acetylene is most common chemical heat source, right? No. So this is used in a chemical gas flame. So in the presence of excess oxygen, it burns according to the reaction. So if you have acetylene and oxygen, what will be the products? You'll have CO2, you'll have H2O, and you'll have some heat. These are exothermic in nature, all those reactions. So if you just do the equilibration, this is 2CO2, right? And once the amount of heat that is liberated, uh, is known, we can roughly estimate the maximum flame temperature with the assumption that that is an adiabatic flame. Okay, so leave these aspects anyhow. Hmm. For question 6, we need to match the followings. There are different welding techniques which I have mentioned over here with uh, some kind of mechanisms needed. Hmm. Which one is the correct one? So once this is done, we will go to some numerical portion. Again, numerical is also a very simple image. Okay. So you have laser beam welding, you have electron beam welding. I have just mentioned it, microplasma welding process, and then you have friction welding. So you need to match the different welding process with their working conditions. So for friction welding, I can see that heat generation by friction. This is as simple as that. So D2. Option 3 is correct. Do you agree? So for electron beam welding, we need a vacuum condition. For laser beam welding, also you need some inert gas ambient condition. I will go through, I will come to that aspect of this weld protection aspect. Are you agree?
Yes, sir.
Okay. Okay. So let us first discuss a little bit on those gas metal reactions or protection of molecule, how we protect the molecule, right? And then we will move to the numerical part. So absorption of gas in whirlpool from the arc or gas flame, they play very important role in most of the fusion welding process, right? So this is due to possibility of reaction between the gas and the liquid metal in the whirlpool. There will always be reaction between those gases and the liquid metal in the whirlpool, right? And the chances of such a reaction are enhanced by high temperature of the metal. So high temperature enhance this possibility of reaction. Now there can be two different types of reaction. So in one type, the gas may just get dissolved in the liquid metal, and what happen in the second type, the gas and liquid metal may react chemically to form some stable compound. You know? So at one case it can completely dissolve, and another case they can form some stable compound by reacting with one another, right? So in such a case where you'll come up with some stable compound, the situation may be considerably different depending on the uh, degree of solubility of your reaction product in the whirlpool, right? As long as your reaction product is soluble, it does not prevent the formation of a whirlpool. So, however, it will result in some embrittlement of the weld joint, right? So, yeah, it will result in some embrittlement. Now, an insoluble reaction, if it happens with some insoluble reaction, the product produces it can be either slag or some kind of surface things, right? And thus they physically interfere with formation of those whirlpool. And in those cases, either the excess gas to the whirlpool is prevented or some kind of flux is used to dissolve or disperse those reaction product, right? Now when the gas gets dissolved in the liquid metal pool, uh, there will be obviously no hindrance towards the formation of the whirlpool because it is getting dissolved. However, if solubility decreases, uh, let's say you are doing some cooling and your solubility gets decreased, uh, there will be some kind of degasification starts, right? So there will be some suitable nuclei formation will be there. There will be some bubble formation will be there, and if those bubbles are trapped, then the quality of the weld will be very poor, right? And also this degasification makes the joint very porous in nature. These are very common defects in a metal whose oxides are easily reducible by hydrogen or can be avoided by the addition of some kind of deoxidant. If you are adding some kind of suitable deoxidant materials in the filler metal, those oxide formations can be avoided, right? Okay, let me drink some water.
Sir, can we ask assignment questions in this session?
Uh, yes and no also. You can ask. Actually, this session is getting conducted uh, to to have some benefits for your assignment questions only. Uh, that is the primary objective why we are taking those live sessions as a PML school. So is this fulfilling your assignment questions to solve these discussions?
Yes, sir.
Actually, I do not have access of what assignment questions are there. I have some previous assignment questions, but anyhow. Okay. So I was talking about this chemical reaction. I was talking about this chemical reaction in welding. So as I was saying, you always will have uh, air entrapment in welding. So you'll have nitrogen, you'll have oxygen and hydrogen gases that can dissolve in your weld metal during welding, right? So these elements usually come from air, of course, and the consumables such as shielding gas and flux, or the workpiece such as uh, the moist or dirt on its surface, right? From these things, this element come from. Now, what are different techniques for protection from this air? What are different techniques that can be used to protect the whirlpool during your fusion welding? So, in case of gas tungsten arc welding or gas metal arc welding, those are typically the cleanest arc welding process. So, by saying this, I am also answering this question: which one of the following is the cleanest weld? Is it gas tungsten arc welding or shielded metal arc welding, submerged arc welding, or gas metal arc welding? So, yeah. So, over those processes, you will use some kind of inert shielding gas, right? So, in gas tungsten arc welding or gas metal arc welding, we use inert shielding gas. Can you name few inert shielding gases which are used as a protection of whirlpool? Just one.
Argon, helium,
Sorry.
argon.
Hmm. Yeah, we can have argon. We can have helium as an inert shielding gas, and they basically produce a short, stable arc, right? So gas shielding through the torch is sufficient for welding most materials. You can do some additional gas shielding to protect the solidified metal, right? But still, hot weld is often provided both behind the torch and under the weld of highly reactive metals such as titanium or aluminum, right? So, yeah. So basically, your welding should be conducted inside a spatially gas-filled box, right? Now, what happens in shielded metal arc welding? So in shielded metal arc welding, the flow of gas in that process is not as well directed towards the weld pool as the flow of inert gas in gas tungsten or gas metal. Right? The protection is affordable for weld metal, but is less effective. Because this is less effective, that results in higher weld oxygen and nitrogen concentration level. Right? You can have some kind of self-shielding arc welding also. So in self-shielding arc welding, you use some strong nitride formers, such as you can use aluminum, or you can use titanium, or you can use zirconium in the electrode wire. right? You can use those elements in your electrode wire alone to protect against the nitrogen. Those are strong nitride forms, right? And since these nitride formers are also strong deoxidizers, the weld oxygen's levels will be slightly lower in shielded metal arc welding. But in submerged arc welding, what will happen? The weld oxygen level in submerged arc welds can vary significantly depending on what is your composition of the flux, or the very high oxygen levels associated with your acidic flux that contains large percentage of silicon oxide, right? So you know that you are using some SiO2 fluxes in submerged arc welding, which is a source of oxygen itself, right? And those are the result of SiO2 decomposition. Now, again, if you try to draw some graph of in terms of oxygen percentage or nitrogen percentage in different types of wells, so this is nitrogen percentage, this is oxygen percentage. So we have at the corner we have gas tungsten arc welding, very low level of nitrogen and oxygen level with very good bit of protection of argon and helium in a shielding gas. Then you have gas metal arc welding, where you can use CO2 also as a shielding gas. And then you can have shielded metal arc welding. You can have some shell plate shielding. And the worst one will be with high amount of oxygen. That will be submerged arc welding, right? Okay. So we have over here A is true. Let's answer question 9, and then finally I will move to these two numericals. So in question 9, the question is the large difference in the solubility of the gases in the liquid and solid states of the metal during fusion welding, that leads to what?
Sir, B, all of these.
All of this
Porosity.
it is C. Yeah. So this penetration and cracks is nothing to do with your solubility of gas. Uh, the gas entrapment will of course leads to this porosity in your weld metal. There are different reasons for this crack formation, other reasons for this crack formation or lack of penetration and all those things. Maybe we'll cover in different lectures. But if you are talking about gas entrapment or the higher amount or higher concentration of oxygen, nitrogen, hydrogen in your weld metal, this will of course uh, and you will of course end up with some increased amount of porosity in your weld metal. Okay, so C is true. Now let's move to question 7 and 8. The remaining portion. Let me first remove this. Question 8 is very simple. Just give it a try. I say this is a 2 kilowatt laser beam. Okay. So you know the power which is focused on a 2 mm dia spot area. So you know the dia over which this is getting focused. You know the time also for which the focusing or the processing is taking place. So I'm asking what will be the energy density for the process. And also I'm saying that my weld penetration depth is 2 mm. That will be required during the calculation. What is required for this numerical, if you want to estimate the energy density for the process, what is required? What is energy density?
Energy by volume.
Energy per volume. Right. Then how do you calculate energy and how will you calculate volume of the molten metal? So power is provided, right? My power is provided as 2 kilowatt. So, and time is provided as 2 seconds. Can you estimate energy over here? What is energy?
Power into time.
The power into time.
Energy is power into time. So what is my energy over here then? This is 4 kilojoule, right? Or 4000 joule. Agreed? Now, if I'm telling that my laser beam is focused on a 2 mm diameter spot area and my weld penetration depth is of 2 mm, so how will you roughly estimate the volume of the molten metal? So if you're thinking it of as a cylinder, simply pi r square h. That would be my volume of the molten metal. How much it is coming? Do anyone have calculator? And please be with your calculator now from the next onwards.
3.18 into 10 to the power 11.
3.18 into 10 to the power 11. This is volume.
No, sir, sorry, I got it wrong.
Check the unit. So this is somewhere around 3.14 into 1 square into 2. So somewhere around 6 mm
6.28.
cube. 6.6.28.
28.
Okay. Let me take one after 6.3 mm cube. So what is my energy density then? So my energy density is 4000 by 6.3 joule per mm cube. Right? How much is this coming?
634.92.
634.92. Okay, I'm assuming you have done correctly. So sorry.
Yes, sir.
So around 635. So this is how we can calculate energy density based on how much energy is there for your process and what is the volume of your voltmeter, right? Okay, coming to the last numerical for today's session. We'll remove this part. Hmm. So I'm saying resistance spot welding of two 1 mm thick metal sheets, which is performed using a welding current of some ampere, 10 kiloampere for some second. So I know the current, which is 10,000, and I know the welding time, which is 0.25 second. What else do I know? This is off. I have a typo mistake. Sorry for that. I know the contact resistance also. So you know the R contact, which is 100 micro ohm. So how much ohm is this?
So 10 to power 6 minus 6.
10 to the minus 6.
10 to the power minus 6. So 1e minus 4 ohm, right? And then what have I mentioned? I have mentioned volume of the weld nugget, which is formed after welding, is V weld is 70 mm cube. Considering the heat required to melt unit volume of metal, so H, let's say I'm mentioning it as H supply is 12 joule per mm cube. So what will be the total heat which is getting supplied?
So 12 joule.
Into volume.
Into 70. So 12 into 70 joule. This is not H supply. This is heat required to melt the metal, right? So considering the heat required to melt the metal. So this is mentioned at 12 joule per mm cube. You know the volume of weld nugget which is getting formed. So you will get to know the what is the total heat which is required to melt the metal, right? That is 840 joule. What I need to determine? I need to determine the thermal efficiency of the process. So how will you define the thermal efficiency? There is two efficiency during a welding process. Maybe in later classes we'll come to know there is something called melting efficiency. There is something called process efficiency or thermal efficiency. So over here, how can you define efficiency? So there will be some amount of heat which is required to melt the material, and I am applying some amount of heat actually for the process. So I came to know what is my H melt, what will be the H supplied for a resistance spot welding process, how much amount of heat you are supplying based on your process current, or the material resistance, and the welding time. These are your parameters through which you will define a resistance for welding process, right? So H supplied or Q or heat flux, how much you are getting is I square RT, you know. So energy is power into time. Power is V into I, right? So from Coulomb's law, can tell that my net heat which is getting supplied is I square RT. So how much you are getting? The total heat which is,
2500 joule.
sorry,
2500 joule.
2500 joule. Okay. So I'm assuming you have done correct. So it is just will be 10,000 that whole square into 1e minus 4 into 0.25. This is 2500 joule, right? So how much is your efficiency then? Thermal efficiency.
33.6.
Understood, right? Okay. So stop over here today, and I expect please attend the sessions. Since if you are missing one session, it will be difficult for you only. Anyway, those this PDFs and the lecture videos will be uploaded later. Okay, if you have any question, you can ask. Otherwise, we'll finish it up over here. Okay. Okay. So we'll meet next Tuesday then. I'm finishing the session. Any question? Okay. Bye bye.